There are many different types of stars out there, some bigger, some smaller than our own sun, which is technically a yellow dwarf. However, it's crucial to know that stars don't have nice, tidy boundaries. They don't have a rigid surface like a rocky planet or moons. Instead, these atomic fireballs have pretty diffuse surfaces, as the superheated mass of gas that makes them up slowly thins out into space voids. What astronomers use in lieu of a surface is a star's photosphere. That's the level at which the star becomes transparent. Therefore, a star's surface means its photosphere. Another important thing to keep in mind is that the volume of any star can't be directly measured. There are various methodologies that do that. Curious to learn more about how we measure volumes of stars and the biggest stars in the universe? Keep watching. Nobody went up to a star with a ruler and started adding up distances in order to measure its volume. What scientists have are estimations, reliable estimations for the most part, but estimations nonetheless. Depending on a range of factors such as distance or structures around stars or between them and Earth, these estimations can be more or less accurate and fall within a smaller or larger area of confidence. The question is there any way we can measure the size of a star more directly? After all, real stellar spectra aren't exactly like those of back bodies, so these rough estimates might be wrong. It turns out that there are several different methods for measuring the size of a star. For example, there's direct imaging, lunar occultation, eclipsing binaries, and interferometry. If you want to measure the size of a star via the direct imaging method, just point your telescope at it and take a picture. Measure the angular size of the star in the image, then multiply by the distance to find the true linear diameter. What's so hard about that? The problem is a phenomenon called diffraction. If you use a real optical system with an aperture of diameter d, light rays won't come to a perfect point at the focus. Instead, interference from rays entering the aperture at different locations will form a fuzzy blob of light surrounded by a series of faint rings, forming a pattern. This pattern is called the Airy pattern after George Airy, Astronomer Royal of England, who first derived the angular size of the central blob and the rings which surround it. The important thing is the angular size of the central blob, measured from its center to the first minimum in the diffraction pattern. It helps to work as far into the ultraviolet as possible, since the decrease in wavelength shrinks the Airy pattern. Unfortunately, the Earth's atmosphere prevents ultraviolet light from reaching the ground. Astronomers have used telescopes in space to take near UV images of very few stars in hopes of resolving them. In at least one case, they have succeeded, barely. As for the lunar occultation method, the basic idea is simple. First, find a star which will be covered by the moon as it moves through the sky. Then, using a high-speed device, measure the light from the star as a function of time, and finally calculate the size of the star from the light curve. The problem is that it appears that any lunar occultation will be a very quick event. One will need a high-speed photometer or camera, capable of hundreds of measurements per second, and a big enough telescope to gather enough photons within each frame to make a decent measurement. This requirement of collecting lots of photons in a very short time is a killer. The lunar occultation method is therefore restricted to relatively bright stars. It's also restricted to stars which happen to lie near the ecliptic, of course. But it's even worse. It turns out that the diffraction makes life difficult for astronomers again. As the moon's limb begins to pass in front of the star's disk, it diffracts the light from the star. As the moon's limb approaches and covers a star, we on Earth see something like this pattern of alternating dark and light spots moving past our detectors. So the light curves, intensity versus time, that we record will be somewhat more complicated than the simple decreasing curve. Fortunately, the moon isn't the only moving knife edge we can use to determine the sizes of stars. There are many instances in which we can use one star as the moving knife edge to measure the size of a second star. All we have to do is find an eclipsing binary system, a pair of stars orbiting around each other, oriented in space so that one star passes in front of the other as seen from the Earth. If we measure the light coming from such a system carefully, we can detect the decrease in total intensity as a portion of one of the stars is covered. Bearing in mind that the diffraction of light waves means that one would have to build an impossibly high telescope to be able to resolve a star like the Sun at a distance of 10 parsecs. It would take a mere hundreds of meters in diameter. But in theory, at least, it is possible to combine the light from several small telescopes separated by a similar distance to achieve the same resolution. This technique is called interferometry. Radio astronomers do it all the time. The shorter the waves, the harder it is to combine them properly. In simple terms, you need to know the distance between the two telescopes to a precision smaller than the wavelength of the light you are combining. To combine optical light waves properly, you need to know the distance between the mirrors to a precision of better than 100 nanometers. That's hard, but not impossible. There are several groups who are currently using optical arrays to do interferometry. One of them is located near Flagstaff, Arizona. Before listing the biggest stars in the universe, be sure to like or dislike the video so that we can continue to improve our content and make these videos better for you. Plus, be sure to subscribe to the channel and don't forget to hit the bell button so that you don't miss any of our weekly videos. Here's the list of the biggest stars in the universe in a descending order. Number 1. The largest one spotted in the universe so far is UY Scuti, a star 9,500 light-years away, close to the center of the Milky Way in the constellation Scutum, meaning shield. It's a dust-enshrouded red supergiant, the largest class of stars out there. That's around 1,700 times larger than our Sun in diameter. It was first spotted in 1860 by astronomers at the Bonn Observatory in Germany, who christened it BD-125055. Subsequent observations showed that BD-125055 grows brighter and dimmer over a 740-day period, so it was classified as a variable star. Variable stars regularly expand and shrink as their brightness changes. Hypergiants are larger than supergiants, which themselves are larger than giant stars. Hypergiants are quite rare and shine brightly. They also lose more mass than smaller stars through stellar winds. To give you an idea of just how huge UY Scuti is, if it replaced the Sun at the center of our solar system, its photosphere would extend past the orbit of Jupiter. The distance from the Sun to Jupiter is approximately 779 million kilometers, or 884 million miles. Gas emanating from the star would form a nebula extending 400 astronomical units. In effect, this would reach far beyond the orbit of Pluto. The average orbiting distance between Pluto and the Sun is 39.5 AU. Number 2. WOH-G64, 1504 to 1730 solar radii, a red hypergiant star in the Large Magellanic Cloud in the constellation Dorado in the southern hemisphere skies, located about 170,000 light-years away from Earth. This star's brightness varies over time, due in part to a torus-shaped cloud of dust that obscures its light. The torus was likely formed by the star during its death throes. WOH-G64 was once more than 25 times the mass of the Sun, but it began to lose mass as it neared exploding as a supernova. Astronomers estimate that it has lost enough component material to make up between 3 and 9 solar systems. Number 3. Mu Cephei, around 1,650 solar radii, a red supergiant in the constellation Cepheus, 9,000 light-years from Earth. With more than 38,000 times the Sun's luminosity, it's also one of the brightest stars in the Milky Way. It appears garnet red and is located at the edge of the icy 1396 Nebula. Since 1943, the spectrum of this star has served as the M2 IA standard by which other stars are classified. Mu Cephei is nearing death. It has begun to fuse helium into carbon, whereas a main sequence star fuses hydrogen into helium. When a supergiant star has converted elements in its core to iron, the core collapses to produce a supernova and the star is destroyed, leaving behind a vast gaseous cloud and a small dense remnant. For a star as massive as Mu Cephei, the remnant is likely to be a black hole. Number 4. V354 Cephei, 1,520 solar radii, a red hypergiant in the constellation Cephei. V354 Cephei is an irregularly variable star, which means that it pulsates on an erratic schedule. It was referred to only by its listings on relatively obscure catalogs. It is too faint to be included in catalogs such as the Henry Draper Catalog or Bonner Durchmusterung. It was included on a 1947 Dearborn Observatory survey as star 41575, but that ID is hardly ever used. Number 5. RW Cephei, 1,535 solar radii, an orange hypergiant in the constellation of Cepheus. RW Cephei is also a semi-regular variable star of type SRD, meaning that it is a slowly varying yellow giant or supergiant. The visual magnitude range is from 6.0 to 7.3. Number 6. Westerlund 1-26, 1,530 to 2,550 solar radii. That's quite a large estimate interval. If the upper estimate is correct, it would dwarf even UY Scuti, and its photosphere would reach farther than Saturn's orbit. Westerlund 1-26 stands out as its temperature varies over time, but not its brightness. Number 7. KY Cygni, 1,420 to 2,850 solar radii, a red supergiant in the constellation Cygnus. The upper estimate is viewed with skepticism as a likely observational error, while the lower one is consistent with other stars from the same survey and with our understanding of stellar evolution. Number 8. VY Canis Majoris, 1,300 to 1,540 solar radii, a red hypergiant star that was previously estimated to be 1,800 to 2,200 solar radii, but that size put it outside the bounds of stellar evolutionary theory and were updated. A hypothetical object traveling at the speed of light would take 6 hours to travel around the star's circumference, compared to 14.5 seconds for the Sun. If placed at the center of the solar system, VY-CMA's surface would extend beyond the orbit of Jupiter, although there still is considerable variation in estimates of the radius, with some making it larger than the orbit of Saturn. Number 9. Betelgeuse, 950 to 1,200 solar radii, a red supergiant in the constellation Orion. Betelgeuse is one of the most well-known stars of its kind, as it's the 9th brightest star in the sky and can easily be seen with the naked eye between October through March on a clear night. It's the closest star to Earth on this list and is expected to go supernova pretty much at any time. Thanks for watching, everyone. Do you know any other observed hypergiant stars? Have you understood the methods by which we can measure the size of different stars? Have you learned anything new from this video? Let me know in the comments below. Be sure to subscribe, and I'll see you next time on the channel.